Hi, I'm Adolph Oliver, and this is the video clip about absolute value equations and inequalities. Now, absolute value equations usually have two answers, and here's how you go about finding them. Let's say that the equation is a simple one just like this. The absolute value of x equals 5. Now, remember that the absolute value, if it's positive inside, it remains positive. If it's negative, it makes it positive. So here's the idea. There are two values of x here that are going to make this work. First off, if we have x equal to 5, okay, then guess what? Absolute value of 5 equals 5. That's great. But you can also have x equal to negative 5. In other words, the absolute value of negative 5 also equals positive 5. So this is a situation we just mentioned here. Absolute value equations usually have two answers, and how you come up with them is simple. You take what's inside of the absolute value and set it equal to the positive of the guy on the right. Here it is, x greater than 5. Or you turn around and take what's inside and set it equal to the minus of what's on the right side. Well, absolute value inequalities, if we don't have an equation but have an inequality, have a range of solutions, and a graph can be used to show the answers. Now, where we're going with this, to talk about two different things that can happen. We can have what I like to call inbound problems, which really have the answers end up being in between. We'll show you what this means in a little bit, but it could look simply something like this. The absolute value of x is less than 3. Okay, when the absolute value is getting smaller, the v is pointing to it, it's heading towards 0, and this is one of these in-between types of situations. How you go about coming up with the answer on something like this is to first change this guy to a regular equation, absolute value of x equals 3, and then find the boundaries from this equation. And as we saw up above, the x inside equals the plus of 3, and it also equals the minus of 3. So these are the two answers that we get if this was an equation instead of an inequality, and they're going to be the boundaries when we come up with this. Now, we said when the inequality was getting, or the absolute value was getting smaller than the right side, in other words, here it is, v is pointing toward it, it's smaller, then we have one of these inbounds. Well, the contrast is the outbound, and that's when we have it look like this. The absolute value of x is getting greater than 3. Well, once again, what we do in this is first change it to an equation, come up with the boundary points, and then we could indicate the outbound solutions. So, the inbound, the absolute value getting smaller, the outbound, the absolute value getting larger, and this is the key to be able to work with these. Okay, well, let's first get a little practice again at working just with the equations. And remember again, here's the idea. You take what's inside the absolute value here and set it equal to the positive of the guy on the right, and you take the inside and set it equal to the negative. So if we do this, one of them is going to be 6x equals, and I'm going to take the positive of the 30, and the other one's going to be what's inside the 6x, and I set it equal to the negative of 30. Remember that if the inside here is positive 30, the absolute value of that is 30. If the inside is negative 30, the absolute value of that is also 30. So that's where these two come from. And of course now it's easy on these guys to come up with the actual solutions here. X equals 5, and this guy right here we're dividing by 6 also, and it looks like x equals negative 5. So our two solutions here for this would simply be negative 5 and positive 5. Now notice both of those would work up here. Negative 5 times 6x will be negative 30. Absolute value, that is 30. That's good. If x is 5, 6 times 5 is 30. Absolute value of that is also positive 30. So you can see very clearly that these are the two guys that are going to work. Okay, here's another example. Absolute value minus 9 equals 2. Okay, well again, what we simply do is take what's inside here, the x minus 9 in this case, and set it equal to the positive of the guy on the right, and the x minus 9, set it equal to the negative guy on the right. And this will give us our two solutions. The minus 9 goes over as plus 9, so x equals 11 would be 1. And then, again, the minus 9 goes over as plus 9. So what we'd have here then is x equals positive 7. Okay, well, let's double check these. We'd, of course, say the answers would be 7 and 11 here. 7 minus 9 is negative 2. Absolute value of that is 2. 11 minus 9 is positive 2. Absolute value of that is 2. So again, you can see that these guys do indeed work out here. Okay, well, let's look at one last example here. Here it comes. And just some more cleaning up that needs to be done. That's all that's going on here. Again, take what's inside, negative 9x plus 3, and set it equal to the positive of this guy. Now the positive is what goes, oops, now wait a second. There's something going on here. Okay, notice this. We've got a negative value here. Can an absolute value ever equal something negative? The answer to an absolute value always has to be something over here that's going to be positive. The lowest it can be is 0, but it can't be negative. So, since this doesn't work, okay, does not work, that means then that there is no solution to this one. Okay, so there we go. So watch out for cases like this. Remember, anytime you have an absolute value, you always have to have a positive guy on the right, because an answer to an absolute value is always going to be positive. Well, as always, anytime you have an inequality, you're going to have a range of answers. And remember, we had the inbound and outbound cases here for the absolute values. Notice here the absolute value is getting larger. So since it's getting larger, this is going to be an outbound answer. So what we need to do first, of course, is find the two boundary points. And those are found by pretending that what we have here for the moment is an equation. So here it is. Now, how do we solve this? Just like we did, guys, previously. We take what's inside here, negative 2n, and set it equal to the positive of this guy. So there it is, plus 10. And we also take what's inside, negative 2n, and set it equal to the negative of the guy. Well, solve this. Divide both sides by negative 2, and I get n equals negative 5. And divide both sides by negative 2 here, and it looks like I get n equals positive 5. Okay, well now, here's what your solution is. It's simple to come up with after this. We know that negative 5 is going to be to the left of positive 5. So let's say that this is negative 5 here, and this is positive 5 over here. Now notice, in the original inequality up here, we didn't have the equal bar with the inequality, so since they're strict inequalities, we have to then make circles here, open circles, not solid. Well now, this is outbound. Outbound simply means all you do now is just show the answers going outwards either way. There we go. Okay. Well, if you wanted to write this in set builder notation, you'd have to say something like this. You'd have to say n is going to be less than negative 5, or, since it can be this way or that way, n is greater than positive 5. And then, of course, your set bar, the variable n, and your curly brackets. So once again, there's a graph and a set builder notation. Okay, well, let's take a look at another one of these. Okay, first thing you always look to see, is it an inbound or an outbound? Notice the absolute value is getting larger. So if it's getting larger, then what we have for this, it's an outbound. So once we find the boundaries, we'll simply just graph the solution going outward both directions. Well, what we need to do is clean up and get just the absolute value all by itself here. So here's the absolute value being divided by 3. So I'm going to multiply by 3, but I have to do the same thing on the other side also. The 3's cross cancel here, so I end up with the absolute value of 8x plus 3 is greater than, well, 2 times 3 is 6. Okay, well now we've got to turn around and come up with our 2 boundary points. So here we go. Remember, what's inside? The 8x plus 3 equals the plus of this. Okay, we pretend it's an equation for the moment. And the 8x plus 3, what's inside again, equals the minus of this. So here we are. These will give us the 2 boundaries so we can make our graph of the solutions. Well, we got to solve these for x. The plus 3 goes over here as negative 3. So I've got 8x equals, looks like it's going to be positive 3. Okay, divide both sides by 8. Here we go. X equals 3/8. Okay, over on the right side, plus 3 goes over as minus 3. So I've got 8x equals negative 9. Divide both sides by 8 again, and I get x equals negative 9/8. Okay, well, there are the 2 boundary points. Now, to make our graph for this, here we go. Notice 3/8 is positive. It's going to be over to the right. Negative 9/8 is negative. It'll be somewhere over to the left. So if I make this right here negative 9/8 and say over here positive 3/8, I've got them in correct numerical order. Go back and take a look again at the inequality. This is one up here. It didn't have the equal bar, so the boundary points have the open circles. And now, of course, we saw right at the beginning it was an outbound. So you simply say, okay, draw the solutions going outward from each of these. Okay, well, lastly again, to make a set builder out of this, we say, let's see, our variable here is x. So we say x, okay, is going to be less than, no equal bar here, negative 9/8, and since it can be one or the other, then we say or x is going to be greater than 3/8. Okay, so, and of course, do your such that line, the variable's x, put your curly brackets to indicate it's a set of answers, and there we go. So here it is as a graph, here it is as set builder notation. Okay, a couple more examples, but notice now these guys, okay, are going to be not outbounds but inbounds. Notice that the absolute value here is getting smaller. So right from that to begin with, we know we've got an inbound, which means our solution will be in between the two boundary points. Well, speaking about boundary points, that's the first thing we have to do. We'll pretend that this is an equation and come up with the two boundary points. Okay, the 4 plus x, here we go, has to equal the positive of this, here it is, and the 4 plus x has to equal the negative of the right. So remember, we're pretending this is an equation to get the boundary points, and we take what's inside here, the 4 plus x, that it equals to the plus of 2 and the minus of 2. Now we got to solve these two guys. Plus 4 comes over as minus 4, so I'm going to have x equals negative 2. There's one of my boundary points. Again, plus 4 comes over as negative 4, so x equals negative 6. Okay, well now, those are the two boundary points. We know it's an inbound, so I can just make my graph line here. Now remember, negative 6 is further to the left than negative 2, so make sure you get these in proper numeric order here. Again, no equal bar on the inequality, so that means that we use the open circles here. But now, since this was an inbound, and remember, we could tell that right to begin with just by looking at the original inequality here, then what we simply do is say, okay, inbound means it's the solutions that are in between, and so there it is as a graph. Now, to indicate what the answer would be, a set builder notation, we could use one of those three-sided guys. Negative 6, okay, no equal bar here, the variable's x, and at the same time it's got to be less than negative 2, again no equal bar. The such that line, our variable x, and the curly brackets. So there it is, either as a graph or as set builder notation. Okay, well now, here's another one, and first thing you got to do, you got to get the inequality all by itself here for this process to work. So this is 2 times the inequality, so what we have to do is get rid of that 2 times, so we're going to divide both sides by 2 here, and that'll give me 3 plus 6b. Now notice, we do have an equal bar here, less than equal to 90 divided by 2 is 45. Okay, so here we are, we got it cleaned up, and since the absolute value is getting smaller, okay, this is an example again of an inbound, and we know that before we even finish up the solution of the whole thing. Okay, to find the boundary points, here we go. Take what's inside, 3 plus 6b, okay, and set it equal to the plus of the guy on the right, and take the same thing, 3 plus 6b, and set it equal to the minus. Okay, solve both of these for the letter b. The plus 3 has to come over as minus 3. So I get 6b equals, let's see, looks like 42. Divide both sides by 6. And looks like we have b equals 7. Okay, there's one of my boundaries. The other guy over here, the plus 3 goes over as negative 3. So I've got 6b equals Well, looks like negative 48. Well, divide both sides by 6. Here we go. And I get B equal to, well, it's negative. And 48 divided by 6 is 8. So here are the two boundary points. Okay, we're all set to get the answer here. Again, make sure you write these guys down in proper numeric order here. The negative 8 will be somewhere over here on the left. The positive 7 somewhere over on the right. So the negative 8 is less than positive 7. Just get them in proper numeric order. Okay, now the original inequality up here. Notice that we had an equal bar, so that means the boundary points are going to be solid. And this is an inbound again. We knew that right from the beginning up here, since the absolute value was smaller. Okay, and then inbound means in between. And so here we are. There it is as a graph. And again, this can be indicated nicely with one of these three-sided guys. Negative 8. Now remember, we got the equal bars on this. So less than equal to, and our variable here is B, less than equal to positive 7. Okay, draw your set line. The variable is B, and there's your curly brackets for the set of answers. Okay, well, there we go.